Hello everyone, welcome back to the second of two lectures in this course. The first on neutron reflectometry, the second on polarized neutrons. If you have listened to the recording or the live presentation of the discussion of neutron reflectometry on Wednesday, we said that we would resume today's lecture with two examples remaining from part 4 of the previous lecture. We did not have time to go into those examples in detail, so that we will finish them now. And after these two examples, we will go on to the second lecture on polarized neutrons. So if you recall where we left off, we were talking about, after spending a significant amount of time discussing how the neutron acts as a probe in diffraction from layered thin film types of structures in what we call reflectometry, we did this because it's important to know what the limitations are and to avoid any possible misinterpretation of the data. You need to be quite careful about this, as you would with any good scientific measurement. Okay, so now we started talking on Wednesday about applications. We discussed some applications in biology, biological lipid membranes and the proteins, the membrane proteins and such, peptides, other biological macromolecules that incorporate themselves in the layer, and how with specular neutron reflectometry we can get very accurate fraction of a nanometer spatial resolution detailed depth profiles along the normal to the film, sort of a cross-section of that film structure. Well, we began to talk about the next of the two remaining examples. This one is an example that of soft condensed matter that's part polymer science, part biology. And this particular example is work that a colleague of ours here at NIST, Ursula Perez-Salas, did several years ago. And she collaborated with a vascular surgeon. His name was Elliot Chaikov from Emory University, Emory Medical University. And he was very interested in developing synthetic veins and arteries that can replace diseased or damaged arteries and veins in people. So it's a medical application, but it involves some fundamental research because those synthetic replacements need to be biocompatible. They need to be such that they aren't rejected by our immune systems. So one of the requirements in developing these artificial vessels is to come up with a coating, a lining that doesn't promote scar tissue, doesn't get rejected, so on and so forth. And one of the issues concerned how the water component is distributed throughout these layers. And if you look at the screen, this slide shows a cross-section of the purported system that was deposited on our substrate that we use for the specular reflection measurements. There's a phospholipid terpolymer layer, there's a polyelectrolyte multilayer, and then there's the chromium gold layers that this is attached to on top of the silicon substrate, our basis of support. So we would like to know, in examining a structural cross-section of this film along this normal, what the distribution in particular is of the water content. So let's see how this went. Here's a more detailed cartoon of the actual molecular constituents of these layers, how they're what they actually look like in atomic detail. And we want to see, presuming this is the correct structure, which we will verify in the course of the experiment, see where water molecules actually reside when placed next to an aqueous reservoir. Here are some data taken, and as we discussed on Wednesday, It's very important in many situations when you're looking at a system that you don't know very much about to have the phase information in that experiment. And so we describe means using reference layers and substrates of extracting from composite systems the reflection amplitude, the real and imaginary parts, the complex reflected wave function itself, which is unambiguous, and has a one-to-one correspondence with the profile that corresponds to these curves. So these are the Q squared times the real parts for some of the data taken in this experiment, and extensive data sets were taken, and you can check in the original publication, the journal article, to get the details. But at the end of the day, after doing with reference structures using different substrates, we were able to extract, Ursula and colleagues were able to find that unambiguously they could solve for what the water fraction was across this system. This is again the normal and the horizontal in this plot, and it shows unequivocally that the water concentration, or the water concentrates in the polyelectrolyte layer up to 40%, and it sort of just is transparent, goes right through the upper two layers and finds its way down here. And this is of great use to the development of these systems. So now let's conclude Wednesday's lecture on neutron reflectometry with one more example. And this is, again, a soft condensed matter material. They're polymer films, but ones that are used as photovoltaic materials, solar cells. So again, neutron reflectometry with soft condensed matter can see hydrogen and deuterium distinctly, and it's a great benefit for any multi-component organic system to be able to label things, hydrogenate this, deuterate that, and so on. The old game that is usually played. So here, what's the question? The question is, if I make a film of these two organic constituents, the P3HT and the PCBM, which is a buckyball with some groups attached to it, when light is incident on such a compound, an exciton is produced. We get a situation where there are electron donors and acceptors, and that capture of the photon creates a current. However, it turns out that this exciton, so-called exciton, which is responsible for conducting the current across the device to create the electricity from the solar absorption of the solar light, this has a diffusion length of the order of 100 angstroms. So how these constituents are distributed relative to one another, what the morphology of the structure, is very important for the operation and efficiency of this device. So it turns out, without going into a lot of detail, which I do not know everything about, one of the ideal structures is this cone-like structure. This is an idealized morphology where this spacing is of the order of 100 angstroms between the P3HT and the buckyball type molecular system. So the question is, can neutron reflectometry be used to actually examine something that was made in the lab and to confirm what the morphology actually is? You can, and then relate that to the electrical performance of the device. So this is what people would like to make. They make something, and the question is, what does it actually look like? So here's where neutron reflectometry plays a role. So to get the phase information in this case, what was done was to do two measurements. One with the photovoltaic film system next to air, and then next to an aqueous reservoir containing deuterated water. So here's the spectrum, the two composite reflectivity systems multiplied by q to the fourth for better presentation. And here on this slide is the real part of the reflection amplitude corresponding to just the film, independent of the air or water backings in the composite system. Similarly, here's the imaginary part, and the data look really good. And if you remember our discussion on Wednesday, or if you look at that, it has a well-defined set of zero crossing points and the two roots of a quadratic equation that has to be solved to extract this imaginary part. And so we know that the neutron is effectively averaging the structure in plane, if there are any inhomogeneities there. It's not an issue. So in this plot is the scattering length density profile. On the left is the substrate, on the right is the air, and in between is the structure of that film, that organic film that we're really interested in learning about. So you can see two plots here, and one in this orange is taking the real part of the reflection amplitude that was obtained from the data for the two composite systems shown on the previous slides, and a direct inversion. Absolutely no adjustable parameters. It was just put into a inversion program using, in fact, this case, the solution of a differential equation by the Sachs method, but equivalent to the Gelfand-Levitin-Marchenko integral equation solution we talked about on Wednesday. And here is the profile. And it turns out that the PCBMs have a higher scattering length density, and they show up clearly a concentration at both the interfaces. So a cartoon rendition of this profile, this scattering length density profiles, looks like something like this. This PCBM material is concentrated next to the silicon substrate as well as next to the air. Now, it turns out that lots of people have a preference, instead of doing the direct inversion solution of the real part of that reflection amplitude that's obtained, to just take the two data sets and simultaneously fit them. And if you do that, it turns out it's a bit more work. You have to, and it takes more time. But the fact is that having those two composite data sets is equivalent in its content of phase information, and nothing is different about what's there. So in doing that simultaneous fitting, when you find the minimum, that's guaranteed. You can show that that will give you the same result as the direct inversion. And people like to do this because they can add additional information that doesn't come from the scattering. For example, they can impose different scattering length densities that are known to reside in the silicon and air or whatever in such a way that that's a constraint. But anyway, the point is, if you do the simultaneous fitting, you get the green curve. And for reflection measurements with this accuracy, obtained, limited by how far out the data was collected in Q, you can see that it was possible to go out to a Q of about almost 0.1 reciprocal angstroms. What happens is that you get exceedingly good agreement within statistical uncertainty by the two methods. So here's an unambiguous, unique profile that's obtained, and people can see that it's not very much like the idealized comb structure at all, and in fact it has this concentration near the interfaces. So that turned out to be very useful for the people making these cells at the University of Delaware. This is just a further illustration of how you can show that, remember that when we truncate data, you get a ringing, you get some oscillations in the data that come from the truncation of the data. It turns out that you'd like to be sure that these concentrations that you see at the interfaces aren't due to those ringing effects, but you can show by simple model calculation that the ringing is very much order of magnitude lower than any of the effects that you observed, and so we're good there. Now, I'm going to stop a second because I see I have a question from Ming. And so I'm going to repeat the question, and he asks, In slide 77, how could you get volume fraction of PCBM in the bulk when you used reflecting geometry? Okay, people also incorporate in this information. They know when they deposit the film how much constituent they have. And so you have to go and take a look at the paper, the actual paper, to see how this was determined. I just frankly don't remember right now. But we were able to convert that scattering length density profile confidently to the composition profile based on what we knew we started with in making the film. I hope that answers your question, but if not, take a look at the paper, and then if you aren't satisfied by what's said in the paper, please email me. Okay? I'm waiting for you to, okay. All right? Thanks. It was an excellent question, because we always have to remember that there is a difference between the scattering length density profile and the actual composition profile that we extract. Remember, the scattering length density profile is the product of the composition profile, essentially, times the distribution of scattering lengths associated with the constituent scatterers. Okay. So now there are appendices that you can look at that we talked, relating to some of the topics we talked about on neutron reflectometry on Wednesday. And they show you a little bit more of the mathematics and arriving at some of the equations, some of the results. There's another set of equations showing how you can get a direct connection between reflection amplitude and scattering density distribution. And some references. And now we're ready to move on to the second lecture. So Mayun, if you will, please load the second one. We are ready to go. Okay, thank you, Mayun. And now we will begin the second lecture. This involves, again, reflectometry, but specifically addresses issues with polarized neutrons. Now, polarized neutrons are extremely valuable in studies of magnetic systems, to look at magnetic moments, magnetic atomic moments and their distribution in different materials that may have some ferromagnetic or antiferromagnetic order or some other complicated structure. And almost everything we know about magnetic systems and hard condensed matter has been obtained by neutron diffraction, neutron reflectivity, or some inelastic scattering techniques using neutrons. However, there are very important applications of polarized neutrons in soft condensed matter. Quite obviously, if you have a soft condensed matter system that has a magnetic component to it, and that is an organic magnet, then you're going to use neutrons, polarized neutrons, to help you study the structure of that system. But today, I'm going to focus on those applications of polarized neutrons that occur in soft condensed matter, where the soft condensed matter system is not in itself magnetic. Okay. So this talk is also divided into 4 parts. The first part is something about neutron polarization and some fundamental ideas. Then there's a brief discussion of the application of polarized neutrons, how they actually are used in magnetic structures, in determining the magnetic structures of hard condensed matter. But we will make this a very brief discussion. Unless somebody has a particular question or has an interest, we won't dwell on this. Now, part 3 discusses how we can use polarized neutrons and ferromagnetic reference layers to achieve the phase sensitivity that we require in getting unique answers to some of those scattering length density profiles. It turns out to be a very important non-invasive means of studying these systems. And then in part 4, we'll talk about application of polarized neutrons for measuring very small momentum or even energy transfers. And unfortunately, because of the government shutdown and the fact that we were not able to give these lectures in the appropriate sequence, This would have been really nice to talk about prior to Professor Dieter Richter's talk on neutron spin echo. But you can look at this lecture and then look at on tape and then look at Professor Richter's lecture again, and this may help clarify some points, or maybe not. Okay, so neutrons have a magnetic moment, and therefore they have a spin. They're spin half particles called fermions, but they are quantum objects. So this spin and angular momentum is quantized, just like in atoms or in electrons. So a neutron has two possible spin states. We call them either up or down or plus or minus. There are two spin eigenstates, and you'll see in the quantum mechanics that it's one or the other. It turns out that because the neutron has a spin, the neutron nucleus interaction, the nuclear scattering, this potential, can be spin dependent in certain cases depending on the spin of the nucleus. And there is a magnetic interaction between the neutron spin and the unpaired electrons in the unit cell of some material. And it turns out that this magnetic interaction is often comparable in magnitude to that of the nuclear interaction. So it's a very strong, relatively strong interaction or potential. The magnetic interaction is very useful, of course, for studying magnetic structures, but as we'll see, we can use the interference of this scattering with the nuclear scattering for experimental measurement purposes of non-magnetic systems. So here's the neutron. The one-dimensional, or the picture of a neutron wave function, not as a plane wave, but as this spinner having two components, spin up and spin down, represented by a pair of equations, actually. And this first part represents spin up, this represents spin down, and it turns out that when the neutron is in a magnetic field, either an applied external laboratory field or a field created by the atomic moments in a material, the refractive index is actually it's birefringent. There are two terms now. There's the nuclear part, this nuclear potential, but there's plus or minus a Zeeman term, the moment of the neutron times the magnitude of the field, the induction actually, in that material or part of space, region of space, where a field exists. So now we have a refractive index where for one spin state, you will get an addition of the nuclear and the magnetic parts, and for another spin state, when everything is saturated and the moment is parallel to the field line, you will get a difference, and it can be made to cancel. And as you'll see in a few minutes, this is a very good way of polarizing a beam. Okay, so things get a little bit more complicated, but with that additional complication comes an enhanced sensitivity, and that we can take advantage of. So we can take advantage of this. Now remember from our lecture on Wednesday in our discussion of how we solve the one-dimensional Schrödinger equation from arbitrary structures of complicated shape and constitution, we solved the one-dimensional Schrödinger equation for specular reflection where all momentum transfer is normal to the plane of the film, and we got the depth profile. Well, the same thing can be done when the neutrons are polarized and we're dealing with magnetic materials, but now that 2x2 transfer matrix and pair of differential equations now gives rise to a transfer matrix that has 4 components, and that comes about by consideration of the spinner and the two possible spin eigenstates. But if you look at this pair of differential equations that you start from, it's clear that what this does is also take into account the possibility that when a neutron, let's say it's in the spin-up spin state, interacts with a magnetic system, it can come back out as a spin-up neutron or not. There is the possibility that that neutron can get transformed from the spin-up state to the spin-down state, the process which we call spin flip. And so this equation you see for the plus component primarily also has a term for the minus component, taking into account a potential term, this rho 1, 2, that is the probability essentially for the spin being changed from plus to minus in that interaction. So I think you'll get the picture of this, I think, as we proceed here. So the potential, unfortunately, is a bit more complicated. It's not a scalar quantity. We have to treat the neutron moment as an operator, in fact, for this spinor system. And the operator is made up of the so-called Pauli matrices, who discovered how this all works out. And you can read about this. I recommend, if you're interested, to read this discussion of spin half in this quantum mechanics book by Eugen Merzbacher. I think it's in one of the references someplace at the end of this discussion, or in one of the other references. So this complicated interaction is described by this operator dotted with the vector B field, which again can arise from an external field applied in the laboratory or from the atomic moment distribution in a solid. And it turns out that we have the same relationship between the transmission amplitudes, the reflection amplitudes, and the incident amplitudes, but now they have a subscript indicating what spin state they correspond to. We have to talk about transmission and reflection for spin up and for spin down. And so now instead of a 2x2 transfer matrix, we have a 4x4, but at the end of the day, that transfer matrix still contains all the information about the material that's causing the scattering. It involves the refractive indices, as we saw, have both a nuclear and a magnetic potential component. So if we solve this by modeling the reflectometry data with spin up, spin down, all of the possibilities, spin up to spin down to spin up, spin up to spin up, and spin down to spin down, we can in fact solve not only for the chemical composition of the material film system, but also its magnetization distribution, both in direction and magnitude. Just want to mention that we usually treat in reflectometry in the low Q limit the material potential as a continuum, and therefore the scattering length density for the nuclear interaction is constant. But in fact, if we go to high enough wave vector transfer, the magnetic component, the magnetic scattering length density, actually falls off with increasing Q. And that is because, unlike the nuclear scattering, which is concentrated in a tiny, tiny volume compared to the unit atomic cell, it's in the nucleus, 1,000 times, 3 orders of magnitude smaller volume of that order. This is spread out across the unit cell. These unpaired spins have a distribution that has angstrom dimension, and so it falls off with increasing Q. This is just a relationship between how things go from real space to reciprocal space. But it turns out, after all that's being said, that since we're limiting ourselves to very low Q for reflectometry applications, this change is usually negligible, and we don't worry about it too much. Okay, so now we have to think a little bit hard here and talk about how we describe neutron polarization. Now, since it's a quantum system, this neutron spin can only exist in one of two eigenstates, as we mentioned already, spin up or spin down. But it's possible for a beam to have a polarization that has a continuum of values. And that is because in a beam, you could have some population of spin up and some population of spin down that's not 50-50 or not 100% one and 100% the other, but it can be some situation in between. So the concept of polarization that applies to a beam, an ensemble of these single neutrons in their respective spin eigenstates, can be discussed. And so that when we're in a state, for example, where the coefficients of the two spinors for spin up and spin down, these C quantities, are not exactly 1 or 0, then we can talk about a polarization for a beam at least that is a statistical quantity that depends on the distribution of these states in the beam. So it turns out this polarization vector can be visualized as we do a classical one, as a classical vector that makes some angle theta and phi relative to a fixed laboratory coordinate system. Or it can be written in terms of these coefficients of the wave function that we showed on a previous slide, C plus and C minus. And it turns out in this table, if you look, for example, again, something polarized along the quantization axis, which is defined by the magnetic field direction at that point in space and time. C plus for PZ equal to 1 is 1. For the minus spin state, C minus is 1. And for a state which, for example, is in the P lying in the x direction, then there's equal amplitudes for C plus and C minus, 1 over the square root of 2, and so on and so forth. Okay, so we can think about polarization rotation. Since it is, again, the polarization is described by a vector in real space, then depending on how the fields are applied and how the neutron spins are how the beam is polarized, for example, we can create situations where we have a polarization in one direction, say along the y-axis, and then by the application of a field orthogonal to this, let's say sticking out of the plane of the slide, we can affect a rotation that takes the neutron polarization from pointing along the y-axis over some distance or time to pointing along the x direction. So again, these coefficients, these complex quantities, C plus and C minus, can be examined to see how to make the spin, the polarization of the beam rotate. And it turns out, if you go through the math, the y component of polarization, in this case illustrated at the top of the page, varies with distance, r, along this path of the neutron, parallel to its propagation direction, k. It varies as the cosine of the argument of where the argument consists of the difference between the refractive indices for spin up and spin down, its propagation wave vector magnitude, and the distance over which it is interacting with that field. So we'll see how this is useful later on. And one thing we want to talk about, and that you've heard from Professor Richter about how useful the precession of polarization can be. Just take this simple example, starting from the left here, and imagine the beam of neutrons propagating from left to right. Well, if we start in a field where the beam is polarized perfectly in the plus direction, plus spin state along the z-axis in this vertical direction, and then we abruptly enter a region of space where the field is now pointing orthogonal to that, say along the minus y direction, then the neutron polarization, according to the formula on the preceding slide, will slowly rotate, or quickly rotate, depending on the magnitude of the field, into another direction. And if I then abruptly come out back into another region of space here, beginning at this point, where the field is again, quantization axis is again along the z direction, well, that z component that's left in that direction will stay constant, but its projection will precess. It will rotate around in the xy plane with the so-called Larmor precession frequency. So now, if we look at this slide tells us how we create a polarized beam. The way a beam is polarized is the following, typically. You can take a magnetic film deposited on a substrate or self-supporting, and if a beam is incident at some glancing angle, if it's a magnetic material, there are two scattering length density components, the nuclear part and the magnetic part. And the sum of these two will correspond to neutrons that are in the spin-up state, and the difference will correspond to those in the downspin state. So if I pick the materials, the nuclear and magnetic parts, to be such that these are equal, one of the spin states will effectively see no film, and the beam will go straight through that film, totally undeviated. The other spin state will see a potential of that film, a scattering length density, that's the sum of the two, and be specularly reflected up to this critical angle that we talked about last Wednesday. And so in this reflected beam is purely spin up, and in a transmitted beam is purely spin down, and we've now spatially separated the incident beam into two subbeams, each having perfect polarization, spin up and spin down. Okay, part 2. So we're just going to talk a little bit how being able to do experiments, reflectometry experiments with polarized beams, how we are able to in fact deduce magnetic structures in hard condensed matter. So here's one of the most useful geometries or configurations for studying magnetic systems. Imagine, if you will, a layered structure extending back along this line into the depth of the slide. And this film consists of atomic planes, one after the other, some of which are non-magnetic, indicated by the blue here, and some of which are not only have a chemical scattering, or rather a nuclear scattering length density, but also have a net magnetization. So this plane has a ferromagnetic component pointing in this 45-degree angle direction. The next one has one that's orthogonal to that, and then this third plane repeats the first, and so on, as an example. Well, if we polarize the neutron beam to be parallel to the vertical axis along some quantization axis in an applied external field outside of the sample, and scatter with the specular geometry Q normal to the film, and then look at what comes out, it turns out that all of the neutrons that scatter in the non-spin flip mode, in other words, they come in as plus and go out as plus, or come in as minus and go out as minus, couple to the vertical component, the projection of the magnetization along this vertical axis. On the other hand, neutrons that come in and scatter via spin flip processes, so I prepare a beam that's plus and I measure a beam that's minus coming out, they couple to all components of the magnetization projected onto the horizontal plane. So if you think about this a little bit, what does this tell us? It tells us if I measure all the processes, plus, plus, minus, minus, plus, minus, and minus, plus, I can reconstruct from that data, in principle, the fraction of moment that's along the vertical and the fraction along the horizontal in each and every plane as a function of depth down into this layered structure. And these are the two formulas, at least in the Bohr approximation, that represent this process. And you can see that it's because of this interference. The nuclear and the magnetic couple, but the magnetic is modulated by the angle at which this magnetization is oriented relative to the coordinate system. So now, not only do we get from this data and here's the horizontal component from the spin flip, we get not only the magnetization as a function of depth, the magnitude of the moment in the system, but we also get the direction. Okay, I see that there's a question from Ming. Is there any dynamic for the polarized neutron? I mean, will the spin down neutron have the chance to be spinning up without being, I guess, seeing external stimuli? Well, it turns out, I'll try to answer the question this way, that if you remove the magnetic field, there is no difference between spin up and spin down. There is no magnetic interaction, so the neutron is really in an undetermined state. Okay, so the only way that we can distinguish whether we have spin up or spin down or some other intermediate state is to have the neutron in some magnetic field. Yes, very good, Ming, like spin in NMR. Okay, now let's go on. And so now we see the great power of this, how we're able to get this information about the magnetization, magnitude, and direction. There are some other selection rules that are very useful, and it turns out that the three vectors of importance are the neutron polarization, the beam polarization direction, the wave vector transfer Q, and the magnetization or magnetic field B or M. So that triad of vectors, when you examine them, the relationship to one another, gives us a set of selection rules that are very useful. And we won't discuss these in detail, but if you have any questions, just email me or look in some of the references. Okay, and just to summarize here, if we have a ferromagnetic system, if I look at the non-spin flip scattering, there's an interference between the nuclear and magnetic, and I see for plus plus and minus minus a difference, and that is because in one case we get an addition of nuclear and magnetic potentials, in the other case we get a difference, and so one is bigger than the other. You'll notice that there's no spin flip, no plus minus or minus plus scattering here, and that is because all of the magnetic components are vertical. There's no horizontal projection. If there is a horizontal projection, in the second example for an antiferromagnetic system, in this case oriented along the horizontal, we get only spin flip scattering that's magnetic. There's a nuclear part here, but this is the same for plus plus and minus minus, and just represents the chemical composition profile along the depth along Z. But the magnetic part is all in the spin flip channel, and you see here a very large peak. This corresponds to 2 pi over the periodicity of the structure. In this case, this peak for the ferromagnetic case is 2 pi over the distance between these planes. Here, we see an additional peak with double that periodicity. And the meaning of that is that now for the magnetic system, the unit cell is doubled. It's not the chemical cell, it's this plus this is one repeat. So twice the distance in real space means half the distance in reciprocal space, and we get a magnetic peak appearing at this half position. And then you can, of course, have more complicated structures where they're both the magnetic components are along both the vertical. There are magnetic components along vertical and horizontal both, and you get more complicated structures. And even you can determine the helicity of helical structures that spiral into the material. And so I think if you just look at this, you get the idea that this is really an extremely sensitive and powerful technique for deducing the structures of magnetic systems, what the magnetic architecture is. This is what a polarized beam instrument reflectometer actually looks like. And it's the same as an ordinary reflectometer, except that in addition to the monochromator and the angular divergence defining masks or apertures, there are polarizing elements, mirror type elements that act, as we discussed in the previous slide, and devices, magnetic fields that are orthogonal to a guide field that's usually taken to be normal, that can rotate the spin. So it's possible to polarize a beam that's unpolarized into one spin state and have plus incident on the sample, or rotate it 180 degrees and have minus incident on the sample, all from the transmitted beam through that device, so the beam is undeviated in the instrument, which is very convenient experimentally. Similarly, you can take another analyzing mirror and spin flipper and analyze the outcoming spin after reflection. So now you can measure plus, plus, minus, minus, plus, minus, and minus, plus in 4 measurements in that configuration to get all the spin flip and non-spin flip information about the sample. Here is a system that represents an atomic layer-by-layer growth of, let's say, magnetic atoms, maybe iron, for example. Let's say we have 3 layers and then another 3 layers, but they're separated by an intervening layer of 3 atomic planes of a non-magnetic material, which could be a superconductor, a semiconductor, an insulator, whatever system you're interested in. So hard condensed matter physicists have used these synthetic layered systems to study how a magnetic layer interacts with an adjacent magnetic layer across a system where the electrons are in completely different types of states, like in a semiconductor or superconductor or whatever. And this can be varied. The thickness of this intervening layer can be varied. The constituents can be changed. It can be put in different magnetic fields at different temperatures. So this has turned out to be an extremely useful means of studying fundamental magnetic interactions in hard condensed matter. Again, through polarized neutron reflectometry and the ability to make tailored systems to one's own specifications. So just to show you a few examples, here's a system of magnetic layers separated by intervening semiconductor layers, and how the ordering in the magnetic layers is affected by the properties of the electrons in the intervening semiconductor layers. And Henryk Kepa and company at University of Warsaw has done some very beautiful studies giving exquisite detail about the magnetic structures and how they're correlated or not in these systems. That's a function of temperature, magnetic field, spacing, and so on and so forth. And this is a great prototype system for studying the properties of potential magnetic semiconductor materials that would be used in the semiconducting industry, for example, to make so-called spintronic devices where the electron currents are actually polarized. Here's another system. This is a system for which Peter Grunberg and Albert Fert won the Nobel Prize in Physics in 2007. And it turns out that this is used in our hard drives now as a reading device. It's so-called giant magnetoresistance effects, where you can get ferromagnetic layers of iron, for example, to line up parallel or anti-parallel depending on the magnetic field applied across an intervening layer of, let's say, chromium, which is anti-ferromagnetic spin density wave. But the mechanism for this coupling by long-range indirect exchange interaction was actually determined by neutron scattering studies. Here's some thing for you to read about magnetic semiconductor superlattices in case you're interested, but we will now, after just showing you one more, here's an example of how a spiral, a chiral type of rotating system can be determined from the same type of polarized neutron reflectometry experiment. Okay, so let's get back to soft condensed matter. In this part, we're going to talk about how ferromagnetic layers and polarized neutrons can be used in the study of non-magnetic organic systems, specifically by using a ferromagnetic layer, indicated by this gray slab here, that's buried well beneath the system of interest, which happens to be this lipid bilayer, and these, in this case, this protein-type structure that's embedded in the biomembrane. So the idea here is the following. Remember, we talked about on Wednesday the idea of using reference layers or reference substrates to do composite reflectivity measurements for two reference values to be able to isolate uniquely the reflection amplitude that comes from the system of interest, so we can directly invert it or solve simultaneously in such a way that we can get a unique answer, an unambiguous scattering length density profile. So the magnetic system reference is very nice because it doesn't have any connection directly to the study of the system, the inorganic soft condensed matter system of interest. It's buried down here. So if we have a polarized neutron beam incident, we can measure the spin up and spin down if this layer is saturated. So we look at the non-spin flip scattering, get two values for the we get two composite reflectivity data sets from which we can extract the part that we need to solve for this. So again, just to say it one more time, the iron layer saturated, its magnetization saturated in one direction, and the beam polarized either spin up or spin down. gives us two reflectivity data sets, r squared as a function of q, that we can use to solve for the part of the film that we're interested in, this row of Z in the red up here, that's common to both composite systems. Here's an example, an early example, where the iron is located here. There's gold, there's alkane thiol layer, and just water D2O backing. And just for the sake of comparison, many different types of measurements were used. We altered the H2O, D2O, we changed, in one case, the silicon to sapphire, and so on and so forth. But by doing all of these techniques, you can in fact use the reference technique to determine what the iron or the magnetic reference layer is. So it's like using the reference technique twice to determine what your reference will be when you use it to study the system you're really interested in, and so on and so forth. But the point is, it works really well. Again, with the requisite care in preparing that iron system so that you make a uniform density with a sufficiently smooth and flat layer. Okay, so now here is some current data, or relatively recent data, taken by Duncan McGillivray and Stephen Holt and Anton Lebrun and company at various places. And they show, using an iron reference layer, the difference between spin up and spin down, and the data that's collected in both air and D2O, for example. And it shows that there is a huge difference in the spin up and spin down results, so there's a very large sensitivity in this reference system. Here's an example of a system that was studied by these people of this constituent of this is a transmembrane protein, and actually an ion channel material that is has implanted itself across this biomimetic membrane, deposited on gold, under which was buried a magnetic layer. The polarized neutron reflectivity data sets were collected for the composite systems, spin up, spin down, and from this it was possible to determine, after a set of different types of measurements under different conditions, where the material actually resided. And it turns out that this molecule is deeply embedded right across the whole thickness of that bilayer, as we saw in one of the preceding slides right here. So the results of the neutron reflectivity measurements confirm that this molecule, this transmembrane ion channel, actually resides embedded in the layer. Here's another example. In this case, it was of interest to find out whether this particular biomolecule, in this case, this is an antibody, how this orients relative to the membrane. And again, using the polarized neutron phase-sensitive technique with the magnetic reference layer, it was shown pretty convincingly that these molecules embedded in the layer and extended in an upright vertical direction. They did not flop down or lie on top of. They actually insert themselves and extend outwards quite a distance, many angstroms into the material. And here's some statistical analysis, a little more quantitative description. And here's a cartoon picture representing the results, the interpretation of that scattering length density profile that clearly shows this extending out. Oh wow, almost, I forgot how far this was, almost 200 angstroms from the substrate. So it's quite a large molecule, and it's clear that it extends out quite a distance from that 50 or 60 angstrom bilayer membrane. Okay, so I think I've tried to show you some examples to help convince you that neutron reflectometry is very, very powerful technique, especially when phase sensitive to determining these scattering length density profiles from organic systems, biologic or polymer, or photovoltaic, if you like. But now polarized neutrons can also be used to measure some other quantities, namely the very small wave vector direction transfers, very small scattering angles, or as Professor Dieter Richter talked about, measuring very small energy transfers. Since he probably concentrated on energy transfers, I haven't had time to look at his lecture yet, but I will. I will talk primarily today, or discuss with you, the application of those neutron polarization to determining very tiny scattering angles. Okay, and this is work that Roger Pinn and John Felcher and lots of other people here and in Europe, Janos Major, Theo Reckfeldt, have explored, and if you're interested, I encourage you to look at some of their very nice articles in the literature. But let's just talk about the basic idea here for now. Here is, if you imagine, on the left, a beam coming in from left to right, and let's presume we used one of those polarizers to get this beam into a perfect polarized condition along the spin-up, with spin-up along the positive vertical z-axis. Now, if those neutrons continue moving in a field pointing vertically, they will stay in that state indefinitely. But if we insert a region of space, a well-defined region with sharp boundaries, which can be done with flat wire coils, where the field is directed orthogonal to the vertical, then in that region, as we showed in previous slides, the neutron can be made to rotate. And if we choose the thickness of this region, the distance across this region, and the magnitude of the field just right, we can make that polarization rotate from along the z-axis to in plane along the x or y-axis. Then if it enters a field that's still directed along the vertical, this polarization direction will rotate or precess within this region and stop when we come out and rotate back up into the vertical direction. So here's a means of using this rotation across this distance in this fixed uniform field as sort of a gauge, as a measuring device. In other words, the number of rotations that occur, the number of precessions within this region depend on the distance in the region, the thickness or length of the region, the magnitude of the field, and the velocity, the speed that the neutron has in traversing that distance. So again, this polarization in this y direction now is given by the cosine of this difference in the refractive indices for spin up and spin down, which turns out to be proportional to the magnetic field. And it's a product of that, of its wavelength and the distance coming across. And imagine a neutron coming straight across with all these field and distance and speed parameters adjusted so we make an integral number of rotations. We go around, let's say, 3,610 times across this distance. But then we look at a neutron from a sample that's been scattered at some angle phi, some scattering angle, and now what's different here? What's different is that the path length is longer. The field's the same, the neutron velocity or speed is the same, but now it's longer, so it turns out for an angle of the order of a degree, it makes 3,610 and a half rotations, but that's 180 degrees out of phase. That's a huge difference. So if we have a device like this rotator to measure what that rotation was in the lab, we have a means for determining scattering angle that doesn't depend on measuring the angle directly. Okay. Now things get a little bit more complicated, a little more sophisticated here. Suppose that I have a machine where neutrons are scarce commodity, and I don't have very many neutrons in the beam, and I want to measure very, very accurately the momentum transfer, the scattering angle, say, of a neutron beam when it interacts with a sample. So I want to see how far it's scattered up or down or whatever. But I don't want to collimate the beam such that it's so narrow in angular divergence that it basically makes the intensity so low that the experiment can't be done. It's prohibitive. So if I want very good angular resolution, I have to have an aperture in the detector that's very, very narrow to see accurately how far that beam has been deviated from the incident direction. But if that can't be done conventionally, then it turns out that I can throw the collimation away, basically. And I can have a relatively divergent beam and use that to get very high accuracy in the angular deviation and measurement of the scattering angle by this technique. So in the previous slide we discussed how the number of rotations are affected by the angle through which the beam traverses a precession field region. Well, imagine that you have a divergent beam, angles down, across, and up, coming through a precession region so that when it gets the neutrons, when they're rotated down to precess in this plane, when they enter this region, some will turn farther than others depending on the path length. If there's no sample here, and I look at the polarization at this point, the polarization, the spins when they come out of here, because of their different path lengths, will no longer be lined up. They'll come out with a distribution. But if there's no sample, nothing happens across this zero field region. If they come to an identical precession region, but in size and shape, but the difference is that the magnetic field is applied in exactly the opposite direction as the first field, then those neutron polarizations that are now out of alignment will rotate back the same amount but in the opposite direction. So at the end of the day, when it comes back out, all of those spins will be perfectly lined up again. And this is called spin echo. So if you have listened to Professor Richter's lecture, you will know about this already. But this is just the basic idea of spin echo. So I can have a very divergent beam, have these neutrons precess all over the place depending on the angles that they're incident at, and then put them all back together. So how can we use this? Well, imagine now we have this set up and we put a sample here. Well, if a neutron comes in, let's just look at the horizontal trajectory for the time being. That will rotate such certain amount, and if we didn't have a sample and it continued on its horizontal trajectory in this reversed field, it would come right back up to its original position. Okay, just as is shown here. But if I put a sample in and the sample scatters this horizontal incident neutron beam up or down, then because these angles are not replicated in this region from what they were in the incident region, there will no longer be a perfect echo condition and the polarization will not go back to its original state of unity. So now a sample messes things up, but the way that it messes up this echo condition is very useful because it encodes in that messing up information about how big the scattering angle was in interacting with that sample. So lots of things can be done now. We can go and we can arrange these precession regions in such a way that we can look at the scattering from a sample and encode in that scattering, and have that scattering angle rather encoded by the amount of polarization change that's measured in the final beam in the detector as opposed to what was incident. And for example, again, we can't go into any detail here, but suppose I put a grating structure here, a periodic structure that an incident beam is on and diffracts from and creates this diffraction pattern. Now, conventionally, I could take a very narrow slit and just move it across this detector and measure at one, or use a position-sensitive detector and record the position so that we can directly see this diffraction pattern. But suppose we didn't have this and we wanted to just have this all go into one detector that had no angular discrimination spatially. Well, we could measure the polarization as a function of different applied fields, and in fact set up a simultaneous set of equations where that polarization rotation in those precession fields acts as a modulation function. And if we measure this measure the scattered intensity recorded, integrated in a whole detector, but as a function of the applied field or the tilt angles of those precession regions, then we can establish a set of simultaneous equations which can be solved for the reflection amplitude. That's a function of that scattering angle by the final and incident angles, the difference in the final and incident angles. So the precessions, so if we write this in integral form, it looks something like this. The polarization as a function of either the field or the length of the precession field regions gives us an integral relationship, a cosine transform with the reflectivity of that grading structure. And so by adjusting again the parameters, either B or the angle of tilt of the precession regions, we can collect data in such a way that we have lots of different modulations, or lots of different numbers of rotations at different angles of scattering, and field applications. And actually, from that set of simultaneous equations, here's a model I did just to show that it works. Reconstruct the original diffraction pattern that we would have seen by other means, by actually measuring the positions of the reflected intensities on the screen. But here it was done without any such mechanism. Just a single detector was put there, and intensity was measured. Polarization was determined as a function of those so-called spin echo length parameter. Okay, so I think you see how this works, and here these machines actually in real life are very large devices. These are primarily used for measuring energy transfers in systems that Professor Richter talked about in the preceding lecture. But here is one that's used for tagging angle on the EVA reflectometer at ILL. This is work by Janos Major and Helmut Tosh and John Felcher and Theo Reckfeldt, also Roger Pinn and Mike Fitzsimmons. So I think, oh, I'm sorry, Ming, I see you have a question. I'll repeat the question. How could we decide the rotation direction of the spin under perpendicular field? Is there a right-hand or a left-hand rule? Okay, let's go back. If you look here, what we do is when we rotate this field down, rotate the polarization down into the horizontal plane, as it rotates in here, we don't know what angle it comes out at a priori, but say if we don't know, for example, the magnitude of the field or the object that we're interacting with, but it comes out at some angle. But then if we rotate this back in this spin rotation device, if it comes back exactly parallel to the incident direction, then we know we did exactly an integral number of 360-degree rotations. But say it comes back pointing down. Well, then it came out, it's 1 pi over, it's pi, 180 degrees out of sync across that distance. But we have to have this rotation analyzer in place, the spin rotator, to be able to project out onto a polarizing device what component is along up and down this direction. Now, if it came out 50-50, we'd know the polarization was somewhere along here and so on and so forth. Does that answer your question or give you an idea about how we do that? Okay, so just to reiterate one more time. Anytime we want to measure polarization, we have to have a rotation device and a I don't show it in this picture, but there's a polarization device here that measures this projection of the spin along the z direction. And so a combination of polarizing device or polarization analysis device, a mirror or whatever, in conjunction with this pi flipper, enables us to determine what the polarization of the beam was after it interacted with this region of space. Okay, I believe that we are at the end of the lecture, almost right on time. I just have included here a few references to take a look at, and I thank you all for your attention and for listening. If you have questions, please email me. And I will answer, or try to answer, every email that you send. Okay, thanks very much again for your time, and I hope it was useful. Okay, I'm signing off. Have a good weekend, and hope the rest of the course goes well for all. Goodbye.